this working? No? Hello? Okay. This is going to kind of build on some of the stuff that John was talking about yesterday in terms of sampling and efficient ways to construct our likelihood for the Bayesian analysis, but in the particular case of pulsar timing arrays. And if there are any questions as I'm going through this, if anything seems unfamiliar or doesn't have an analogy with anything that's done in LIGO, then let me know, because I would like to know if any of the methods we developed in pulsar timing arrays can cross over. Or likewise, if anything that's been developed in LIGO can cross over to pulsar timing arrays. So I'll go briefly through how we construct the pulsar timing array likelihood and all of the different signals that appear in there, all of the different noise sources, and then our search strategies for both stochastic and deterministic signals, as you might expect, given that we are expecting that a stochastic background will appear first for pulsar timing arrays. Most of our search strategies and methodologies are aimed towards optimizing that, but we also search for deterministic signals too, things like continuous wave sources and also burst with memory signals. Then I'll go through sampling and model selection, the kind of strategies that we use there, and then finally how we assess detection significance, or how we convince the frequentist community of our Bayes factors, essentially. So first of all, I talked about this a few days ago. The first aim of a pulsar timer is to get a good timing solution. And that means that you take your raw vector of arrival times of pulses and you try to fit a deterministic timing solution to that, which accounts for the period of the pulsar, how fast the pulsar is spinning down, its position on the sky, all properties of the interstellar medium, things like that. And if the pulsar is in a binary system, you have to take into account the orbital parameters of the binary. So the aim is to try to get the raw arrival times, fit a timing model, and then subtract off that. You should be left with something which is just consistent with noise. But if you make an error in the position, you're going to get this kind of feature. If you make an error in the spin down of the pulsar, you'll get this kind of quadratic feature. An unmodeled proper motion of the pulsar will lead to this expanding sine envelope. So this is, sure. Yeah, this is the date. It's in modified Julian date, which is measured from something like 1950. It's a silly thing to do, but it's for astronomers to measure in modified Julian date. To give you an idea, I mean, the current modified Julian date, I think, is 57,000. That's the number of days since a certain reference date. Yeah, this is because the position of the pulsar is being measured through parallax, so this is going to have like a yearly variation, and the same for this. There's you get a sort of yearly, or maybe it's even 6-month variation here, and that's in an envelope because as you're sort of departing further and further away from a good timing solution as time goes on here. So and this makes sense because the spin down of the pulsar appears as a frequency squared term, so you kind of get a quadratic here. So there are reasons why it appears this way. But the goal here is to not produce any of these features. You want something which is initially very close to consistent with noise. So you want to try to subtract out or fit out all of the deterministic intrinsic pulsar stuff before you even try to search for gravitational waves. Yes, yeah. It's both. So we actually analyze something called the post-fit residuals. So we initially fit for a timing solution, but then we include small linear departures of that best fit solution in our model. But it actually doesn't matter. So that's something that had to be worried about before we started doing our Bayesian magic, because in that case they had to work out numerical sort of compensation factors for the fact that they might have been fitting out gravitational wave power. But now we actually, what John was asking, we not only start with the post-fit residuals, but we also account for small departures in case we are sucking out some of that gravitational wave power, we allow for it all to sort of be fitted together in the actual Bayesian analysis. So I will explain all of this and how it factors in. This procedure is done before, and we assume that the gravitational wave signal is small enough and that this is in the, we're sort of in the linear regime where you can make small departures away from the best fit solution just as a linear sort of Taylor expansion, essentially. Yeah. It could contain some gravitational wave power. The point is that it doesn't matter because we're going to reanalyze all of this again in the Bayesian analysis. So this is done by the Pulsar astronomers. They produce this timing fit, and then we just use it as a starting point, essentially. We iterate on it. Yeah, of course. Uh-huh. Yeah. 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 Mm-hmm. Yeah. Mm-hmm. 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 No, it's remarkably difficult because, LIGO is essentially a fixed experiment, and you can take it apart and see what each part is contributing towards the noise budget. But for pulsar timing arrays, it really depends on the exact configuration of pulsars that you use and some unknown physics happening in the pulsars. The best we can do is sort of give a qualitative description of the noise budget when you see the sensitivity curves. Yes. Mm-hmm. Yeah. Mm-hmm. Yeah, I mean, we do have additional noise factors which account for if the pulsar astronomers have made any error in computing the uncertainties on each measurement. We introduce like a multiplicative factor, it's a fudge factor, to correct for what they've done. We also add other sources of noise and quadrature, and that has to be done per receiver. So we have all of these different noise processes per receiver to try to account for any uncertainties in what they've done, or just other sources of noise that we haven't accounted for. And I will talk about that in just a second. So this is what you're starting off from. It's sort of the post-fit timing residuals where you've tried to bring everything to be consistent with just noise. But the kind of noise that we're dealing with, well, we'll initially have some deviations around the best fit timing model. You'll also have some white noise, and that's just from the time of arrival measurement uncertainties. There'll be extra unaccounted for white noise in the receivers, and you'll also have something called pulse phase jitter. And that occurs when you've got a 5-minute observation, which gives you some pulse shape, but that's being compared against a decade averaged template. So the 5-minute one only has a finite number of pulses that it's been folded over, so there'll be some stochastic variability in that folding process when you compare that to something which has been averaged over like a decade. So we have to include this. That's just something we call jitter. There's also intrinsic low-frequency red noise, and that's due to rotational instabilities in the neutron stars themselves. Millisecond pulsars are very stable, but there is still some red noise, and that'll just show up as this very long timescale noise source. So this is correlated over long timescales. There'll also be spatially correlated low-frequency processes, and one of those is the gravitational wave background. That's good. We have a very distinctive signature that we search for, which is the Hellions and Downs curve. But you could get other sources of noise which induce spatial correlations between the pulsars. These are troublesome, and we have to take into account that. So if you've got long timescale stochastic drifts in the time standards that we refer everything to, like the atomic clocks in the observatories or the global clock standard, that can look like something that's correlated between all the pulsars because it's affecting all of the pulsars in the same way. Or you could have uncertainties in the position of the solar system barycenter that can induce some correlation between the pulsar observations as well. So you've got all of these sort of troublesome additional spatially correlated processes, but really you want to try to leverage the Hellions and Downs curve to get out the gravitational wave background. So all of the delays that are departing the time of arrivals from the sort of the deterministic model that we've constructed will be caused by all of these unmodeled phenomena that I've talked about previously. You've got white noise, you've got intrinsic red noise, you've got gravitational wave background, you might have clock errors, all sorts of stuff. But we treat everything, all stochastic processes, as Gaussian stationary. Some people have explored non-Gaussianity of the noise. There are also non-stationary approaches, but by and large, we just treat everything as Gaussian stationary, as I'm sure you all do as well. So the white noise is obviously very simple to write down in the time domain. It'll be associated with some sort of variance, and it'll be uncorrelated between the pulsars. So this is my sort of simple cartoon picture. If you just create a vector of your arrival times, some of the arrival times will be made almost simultaneously. So you don't just have a purely diagonal covariance matrix for the white noise. You might also have blocks. Something will be block diagonal, because within a second, the observations may be completely correlated with each other. So they have this block diagonal structure for the white noise. No. It's still uncorrelated between different pulsars. But if you imagine taking like 100 observations of the same pulsar almost at the same time, then there may be some receiver correlations, which mean that all the observations within that 1 second are correlated. So it's not going to be diagonal noise, it'll be block diagonal noise. You also have some intrinsic low frequency red noise, and that has a dense structure in the covariance matrix. And the gravitational wave background will look also like red noise, except that it'll be correlated between the pulsars in a way that we know, which is the Hellings's and Downs correlations. And the reason why we do this array of pulsars is that we want to be able to separate the intrinsic noise from the gravitational wave background. So this is now an array of pulsars, 1, 2, 3, 4, and within each block, the gravitational wave background appears everywhere. So it appears in the pulsar autocorrelation, and also in the cross correlations between the pulsars. The signal here will be modified by the Hellings's and Downs coefficient for that particular pair. But along the diagonal, you have to worry about the white noise and the red noise in each individual pulsar, which is uncorrelated. That's why they don't appear over here. And yeah, sure. No, keep going, it's good. Mm-hmm. It is both. So we initially use the observatory clock. Then it's referenced to a global time standard. There are lots of global time standards, which I can't even recall all of them. Well, they all have their own either GPS or atomic clocks that they refer to. But then there is a global scientific time. Yeah. If there's some uncertainty in that global time standard, then yes, because they're all being referenced to that. And that's something, instead of looking like the Hellings's and Downs curve, that will look like something which is completely correlated. So it'll be one, because they're all affected in the same way. Yep, yeah. But that's all of these additional spatially correlated things, why we have to use an array of pulsars. So briefly, in sources, you've got the characteristic strain spectrum, which is built up from the individual sources. But what will that actually look like in the spectra of the timing residuals? Well, the characteristic strain spectrum looks as f to the minus 2/3 for a circular, entirely gravitational wave-driven population. When you convert that into the power spectral density of the timing residuals that's induced by the background, it actually looks like f to the minus 13/3. So you're dealing with something which has a very red spectrum. It'll look like something which has power on very low frequencies in your time series. And to convert that into the time domain, you just use it's called the Wiener-Khinchin theorem. If you've never heard of it, I think that's how you pronounce it. I don't know. But it's simply doing a sine transform of the power spectral density to get your dense covariance matrix. Now, the way we used to do the pulsar-timing likelihood was entirely in the time domain with no tricks. So you would have tens of thousands of observations which you had to correlate together, make a gigantic, maybe 20 or 30,000 by 30,000 covariance matrix, and you'd have to invert it every single likelihood evaluation time. What this G matrix does here is it projects you into the null space of the pulsar timing model, and it means you correct for any possible removal of the gravitational wave power when you've done the initial fit. And this dense covariance matrix in here with some parameters which you care about will be composed of the white noise, the intrinsic red noise per pulsar, and then the spatially correlated gravitational wave background. So with the gravitational wave background, as I said, all pulsars are spatially correlated. They induce a dense covariance matrix, and that'll be of dimension number of pulsars multiplied by the number of TOAs per pulsar. And the bottleneck in the likelihood is going to be this matrix inversion, which you have to do every single MCMC sampling. The fastest way to do this, because it's a positive definite matrix, is to use a Cholesky decomposition, but that's still order n cubed for the size of the matrix. So this is very, very expensive. A 10K observation likelihood time takes roughly 20 seconds. The current observation data has 30K observations for just one pulsar. So the full pulsar array could have 60,000 observations. That's just unacceptable. We can't wait around that long. It would take an unreasonable amount of time. So what we do is we describe all of the processes in a rank-reduced formalism. That means that since the gravitational wave background is mostly low frequency, we don't have to really care about the higher frequencies in that. So we can just do essentially a Fourier decomposition of the signal and express it in terms of a few low frequencies. Rank reduced in this way just means that you're describing your signal. Go ahead. Yeah. No, as you add more observations, this makes your matrix larger. It makes your matrix larger in dimension linearly, but the inversion of that matrix goes as n cubed. So it just becomes completely unreasonable. Already is unreasonable. Because you want to do this potentially millions of times. And this would it would take you almost a year just to do a single analysis. So that's unreasonable. We want to do this many, many times in experiment, you know. So we go towards this rank-reduced formalism where you describe your timing residuals as being some combination of lots of different processes which you project onto a set of basis functions or a set of basis matrices. This part accounts for small linear perturbations around your best fit timing model solution for the pulsar. So even though we've subtracted off that best fit solution, we allow it to wiggle around a bit. There's also all low frequency red noise and the gravitational wave background signal, which you project onto a Fourier basis. There's then this jitter matrix, which I won't talk too much about, but it works the same way, and then just white noise. So for this matrix, it's the number of TOAs by the number of timing model parameters. So you've got like the period derivative, lots of different measurements of the dispersion measure as you go on. That accounts for interstellar medium effects. Lots of things like that. The Fourier matrix for all low frequency processes is number of TOAs by twice the number of frequencies, and that's because for each frequency you've got a sine and a cosine. It's a Fourier decomposition. And then this is something which groups the TOAs by epochs. So all of the potentially 100 or 10 observations which are made within a 1 second window are kind of all grouped together. So, like I said, M is a matrix. It's a design matrix, which means it's a matrix of derivatives with respect to the timing model parameters. This is just alternated columns of sines and cosines, and this is block diagonal in structure. So this already gets you down to the sum of, a couple of hundred, a few tens, and a few tens, which is a lot smaller than tens of thousands of observations. So this makes everything a lot faster when we project onto this rank-reduced formalism. So let me just write down the form that this takes. We start off by writing the probability of the noise. We know that this obviously has a very simple structure, and so the form of this noise covariance matrix will have multiplicative factors that we search over to correct for the formal time of arrival measurement uncertainties. So basically, we're assuming that the pulsar astronomers might have got things a bit wrong, so we're correcting for their reported uncertainties. There's also some extra noise which is added in quadrature. That might be if the intrinsic pulsar red noise has a high frequency tail to it, that might show up as an equad, this extra quadrature, extra factor. We can then replace the factors of n here for just subtracting off all of the other processes. So you're just doing n equals delta t minus all of these things. But that's not really all you know. That's the likelihood as it is. But if you actually try to do a search over all of these different coefficients, and you try to search over the Fourier coefficients of the gravitational wave background and all of the red noise parameters, you wouldn't learn anything because you haven't incorporated everything you know. You haven't included your prior knowledge. So let me just group everything together. This is one giant rank-reduced matrix. This is, again, is the timing model, low frequency, and then the jitter. These are all basis matrices, and this is the concatenation of all of your coefficients that you care about. But you're treating everything as a random Gaussian process, so you should incorporate that knowledge into your likelihood. So the probability of these coefficients given some hyperparameters, these are just parameters which encode the variance of these coefficients, and you have to include that as well. Now what we've done here, you might notice that the giant B matrix has an infinity in it, which seems like a bad thing to include in any sort of numerical code. That's because we want to treat the timing model perturbations as having a uniform prior from minus infinity to plus infinity. What we're doing here is just approximating that with a Gaussian with an infinite variance. And it does exactly the same thing in practice. It works great. And we only have to ever have to deal with the inverse of B anyway, so we don't encounter this infinity. So once you include this extra knowledge, things get a lot more interesting. We use hierarchical Bayesian modeling, which means that you sort of tack on these extra probability priors that you know about and build up your model. So this is the initial likelihood that you had that I said you wouldn't learn anything from. But then you've incorporated the fact that you know everything is a random Gaussian process, and then you'll also have some priors on the variances of these coefficients. These, yeah, go ahead. Yeah, of course. I mean, we do essentially. This is the formal way of writing it. We don't ever actually deal with that. So we do have to marginalize over, the goal is to marginalize over these small timing model perturbations. These here? Yes. So, for example, this is the variance of the red noise, both intrinsic and gravitational wave background. So what's going to appear in here will be the amplitude of the background and like the spectral slope of the background. And other sorts of white noise stuff will appear in here. But these parameters here are departures away from the best fit period of the pulsar, the spin down of the pulsar, things that we want to include in the model to allow it to wiggle around a bit, but we're trying to marginalize over those. We don't really want to search for them. Eta, this, or no, where's eta? Eta is your vector of parameters that you're actually going to MCMC over. So like the amplitude of the background, that's your hyperparameters. So things like the amplitude of the background, spectral slope, and all of the different red noise amplitudes and spectral slopes, the EFACs, the E-quads I was talking about, all the white noise stuff. So these are the actual parameters which encode the variance of these different coefficients. Because at the moment, these are still just like Fourier coefficients, but you actually want to search for the power spectral coefficients, and that's what eta does. Delta T is the actual data, so the post residuals, yeah. So after we've done the initial best fit for the timing solution, this is our sort of vector of data, and then we're just allowing that best fit solution to wiggle around. We're allowing it to have some red noise or a gravitational wave background, and then this extra jitter, which is block diagonal in structure. So you're grouping everything together. You're treating the wiggles around the best fit timing solution as having some wide uniform prior, essentially an improper prior, and then you're allowing the variance of these amplitude coefficients, these Fourier coefficients, to have some variance which you're going to parameterize. And the parameters of those variances is going to appear in this vector here, and I'll show you in a second that that's what you actually MCMC over. So you build up your hierarchical model, so the probability of the data given the initial sort of Fourier coefficients multiplied by the probability of those Fourier coefficients given some parameterization of the variance, and then the probability of the parameters which appear in your variance, things like the amplitude of the gravitational wave background or the amplitude of red noise. You can then, because you've tacked a bunch of Gaussians together here, you can analytically marginalize over all of those B coefficients, things which you don't actually care about. So that just incorporates all of the uncertainty in the B coefficients, but you don't have to deal with them anymore. You don't care about them anymore. That gives you a marginalized likelihood where you've marginalized over all of the linear coefficients, and you're back to something which looks like it's dense. So it might seem you haven't actually learned anything, but really what you've done is you've pieced together a bunch of basis matrices and variance matrices into this form. So that's your noise covariance matrix, which is block diagonal or maybe even diagonal in structure, so that's easy to invert. You've then got your basis matrix here, your matrix of variances for all of the different processes, and then the transpose of the basis matrix again. Why have you done this, and what are you actually doing here? Well, if you look at the gravitational wave part of this matrix, all you're doing, because these are sines and cosines, this is the variance of your gravitational wave coefficients. That's just the matrix form of the Wiener-Khinchin theorem, the cosine transform into the time domain, where this is the power spectral density. So that's all what this process is doing. You're just kind of phrasing things as essentially a Fourier summation. That's all you're doing. But it allows you to use something called the Woodbury matrix lemma. When you've got this sort of form of covariance matrix, it allows you to, this is an exact thing, by the way. We haven't made any approximations here. This allows you to write down the inversion as a much lower dimensional process. So the bottleneck will be this inversion in here, but that's only going to be of the size of the number of frequencies that you're modeling the background with, or the number of timing model parameters that you care about. So instead of inverting this, which might have tens of thousands of observations, you just have to invert this, which might be of order 100. So it's a much neater way of doing everything here. It's very easy to do this, and that brings your likelihood evaluation time down a lot. So instead of dealing with 20 to maybe 100 seconds, without including the cross-pulsar correlations, that gets down to tens of milliseconds. And with cross-pulsar correlations, at most, you're dealing with a few seconds here. So this is time profiling of the likelihood when you include spatial correlations. So that's the solid. When you don't include the spatial correlations, that makes the likelihood diagonal in the pulsars. So it's much, much faster. And then obviously it gets, as you include more frequencies in the Fourier summation, that makes the inversion process more expensive too. So this is how we actually do the likelihood evaluation and the pulsar timing searches in practice. It's pretty neat. We've incorporated a bunch of different matrix approximations and things to speed it up. So like I said, this is the matrix, the discretized form of the Wiener-Khinchin theorem. But what does this actually encode? Well, this particular variance is going to be the variance of the red noise coefficients. That red noise could be intrinsic to each pulsar, or it could be include the gravitational wave background as well. So really, this is going to be the gravitational wave background part with the power spectral density of the background. You then have the overlap reduction function, which for an isotropic background is just hellions and downs. And then you've got some additional bit that you tack on the end, which is specific to each pulsar. And it's the intrinsic red noise per pulsar. Yeah, and that's how you relate this row to things like the amplitude of the background and then the spectral index of the background. There are lots of different models we could make for that power spectral density, though. You could have a simple power law for the background. So you've got an amplitude or spectral index. You can just parameterize it as something which floats free per frequency. So you'll actually get a spectrum. That's number of frequencies, obviously, in dimension. And then you could have a turnover spectrum for which I talked about a few days ago. You've got an amplitude, you've got a spectral index, but you'll also have some sort of bend frequency at lower frequencies, and then something which dictates what the slope is at lower frequencies as well. So all of these things are a way of parameterizing the shape of the spectrum, and the goal would be to eventually extract physics from that shape, the physics of the final parsec. So these are some results that we calculated for the nanograph 9-year limit paper. I showed this a few days ago. This is when you lock the high frequency amplitude to some prior, astrophysical prior, and you let the lower frequencies float free. You're trying to see whether the lower frequencies need a turnover in the spectrum. If there's a turnover in the spectrum, that might indicate some final parsec hardening due to the environment. Okay. You can do something very similar with the overlap reduction function. That's something I've worked on quite a lot. And that's the overlap reduction function dictates how much the power decreases when you move your detector, essentially. Or it's the degree of overlap in the power between two different detectors. So there's an overlap reduction function for LIGO Hanford and LIGO Livingston. There's also an overlap reduction function for pulsar-timing arrays, because you'll have one line of sight to one pulsar, but you'll then have another line of sight to a different pulsar. So they'll share some power, but it won't be identical. So there is some characteristic shape which dictates how much the power is reduced. That's just the Hellions and Downs function. And it's really the integral of the antenna pattern overlaps between the pulsars or the detectors, weighted by the angular power distribution of gravitational waves on the sky. So this is the overlap in the antenna patterns between the pulsars, in my particular case, can be any detector, and then it's weighted by the actual power distribution of gravitational waves in the sky. And what you want to do is parameterize this in such a way that you can get some way of looking at the power distribution. So this matrix, which appears in all of our equations for the likelihood, is n pulsar by n pulsar. This is your antenna response matrix, which we can just write down as something which is n pulsar by 2 times the number of pixels, because you'll have plus and cross responses. And then you'll have some diagonal power matrix. You're assuming that there's no correlations between gravitational waves on one side of the sky and gravitational waves on the other side of the sky. For example, black hole binaries on this side of the sky can't know what black hole binaries are doing on this side of the sky. So any power correlation matrix has to be diagonal. So we can just treat this as a diagonal matrix, which is 2n pixels in length. This is something you already know. This is simply from your antenna pattern equations that you can write down. This is something that you want to parameterize. You can do that in a variety of ways. You can decompose the power in the sky with some spherical harmonics, which is the way the CMB community do it. You can just treat this as some large extended region of power in the sky. For example, maybe you have a cluster of galaxies with lots of supermassive black hole binaries in there. You might have a single point source. So this would be like a suboptimal way of searching for single sources, because it's looking at the power instead of the actual phase of the signal. But you could just imagine lighting up a single pixel and using that to search for a single source. Or you could actually do a direct reconstruction of each of the elements of that overlap reduction function matrix. So these are lots of different ways that we can attack anisotropy in the sky and say what the distribution of sources in the sky looks like. I don't have a slide on that. I mean, we're at the moment, because we have nothing, we would be restricted to the very local universe. Most of the information on the sources is coming from redshifts closer than 2. We can't see out that far. So we're dealing with probably redshift of order 0.1, maybe to 0.5. Yeah, that's for our point source. Yeah, it's dealing with something very close. Yes, yeah, if you're dealing with something maybe 10 to the 8 or 10 to the 9 solar masses, then it's not evolving over 10 to 20 years. If you have 10 to the 10 and you have some moderate eccentricity, then yes, it may evolve. in deterministic searches, we always include the pulsar term. Yeah. So to search for deterministic signals, you just need to modify your likelihood by changing factors of delta t, which is your data, to delta t minus your signal model. So remember, this is your data and this is your signal model. We can search for circular binaries. We can search for eccentric binaries. Both of these can include the pulsar term. If you haven't heard of the pulsar term, and I'm not sure I described it a few days ago, the pulsar term is the stamp of the gravitational wave when the gravitational wave passes by the position of the pulsar. So it's actually a snapshot of the black hole binary at an earlier time than when it appears at the Earth. So if you sort of concatenate all of these snapshots, what you get is an image of the black hole binary as it's evolved to the time at the Earth, but then actually much earlier as well. So you can get a picture of the black hole's binary's evolution over potentially thousands of years. And in that case, you do have to take into account things like the binary's evolution, because it is going to be inspiraling, it is going to be changing in its frequency and its orbital separation. So we can search for any type of circular or eccentric binary. We don't include things like spin-orbit coupling. We don't include more sophisticated terms that LIGO obviously has to include. We're just not sensitive to things like that. But we are sensitive to leading order eccentric effects. We can also search for some generic burst. You can potentially imagine a supermassive black hole on a hyperbolic orbit just sort of finding another black hole and sort of slingshotting past it. That might look like a sharp burst of gravitational waves. So this might be a good model for that. Another thing is a burst with memory. Have we talked about bursts with memories? Yeah. So a burst with memory is something that I still have difficulty getting my head around. It's very, very cool. It's the result of a permanent dent in space-time caused by a black hole coalescence. And it causes a sort of DC offset in the metric. So what this looks like is, in the metric, it'll look like just an offset. But in the timing residuals, or in the gravitational wave influence, it's going to look like a ramp. And we have very simple ramp functions, which we can parameterize as a function of the gravitational wave sky location or the ramp time, things like that. Yes. No, we don't see the merger waveform, but we see the burst. We can see the burst with memory. So we are indirectly sensitive to the actual merger. Yeah, but we don't get the actual merger waveform. You've got in-spiral merger and then ring down. We only get the in-spiral part of the direct gravitational waves. But the burst with memory is a signature of the coalescence, which we can also be sensitive to because it's broadband and it's low frequency. Mm-hmm. Yeah. 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 Mm-hmm. Sure. Yeah. Well, the rate of detection of these things is probably very, very low, much lower than you would get for circular binaries or eccentric binaries. But it is plausible that we could catch one. No, there is a grad student at University of Wisconsin-Milwaukee who's working on the rate of burst with memories and also a burst with memory background, which could be detectable in pulsar timing arrays. The level is probably much, much lower than the sort of in-spiral background, but it's still in prep, so I'm not sure if there are any numbers for that. Mm-hmm. So what do you mean? If you detect it through the pulsar term, you mean? Yeah. Yeah. yeah, I think you would have to look for correlations. Okay, so this is what I've dealt with so far is kind of the signal types, stochastic and deterministic, how we structure our likelihood around those different sources. I'll now get on to just a brief discussion of MCMC sampling, and we can expand this if there are any technical questions and stuff. So we're always using a tuned parallel tempering MCMC sampler. We're exploring typically 50 to 100 dimensions. So we're using, in an average experiment, maybe 30 to 40 pulsars. We search over some red noise parameters per pulsar. That gives us maybe 2 parameters per pulsar, which is just intrinsic. And then you're already up to between 50 and 100. Then you've got the additional gravitational wave parameters. There are white noise parameters, those EFACs and the E-quads I talked about, but we fix those at the maximum likelihood values of a single pulsar analysis, which we do beforehand. So before we do an entire examination of the pulsar timing array, we do a noise analysis, fix those white noise parameters. Formally, though, there are roughly 1,000 dimensions because you've got those Fourier coefficients, which we marginalized over because we didn't care, but they are still part of the model. So we've analytically marginalized there. We use a parallel tempering MCMC sampler, which was written by Justin Ellis, and that includes quite a nice cocktail of parallel tempering MCMC, which allows proposals between different temperatures. So you're exploring the full prior, where the higher temperatures sort of decrease your likelihood contrast and allow you to easily explore the boundaries of the parameter space. You can get an in-temperature proposal mixture of differential evolution. Differential evolution is when you take 2 points in the past history of your chain, you then have a vector which is joining those points, and you suggest a new point somewhere along that line. You've got adaptive MCMC. Adaptive MCMC accounts for the fact that it's difficult to know exactly how wide to make your proposal function. So when you propose new points, you have to make some choice of what that proposal distribution is going to look like. If it's too narrow, then you're just going to, if your proposal distribution is too narrow, then you're just going to get stuck around the same point. If it's too large, then you might propose a point which is like up here, where the likelihood value is very low, or down here where it's very low, so you might not actually move at all. So in this case, your acceptance rate for new points will be very, very high, but you won't be exploring the parameter space. In this case, your acceptance rate will be very, very low, and in the same way, you won't be exploring parameter space. So adaptive MCMC takes the past history of the chain. It then looks at the covariance structure of that chain, and then will propose an adaptive jump proposal based on the covariance structure. So essentially, you take, say this is the past history of the chain, some sort of vector in parameter space. You then look at the covariance structure of that. You then do a Cholesky decomposition on that, so you decompose this as some lower triangular matrix multiplied by the transpose of the lower triangular matrix. That's possible because a covariance matrix is positive definite. You then propose a new point in parameter space, but it's actually, it's of the same length of the parameter space, same number of dimensions, but it's actually drawn from a unit variance Gaussian centered around 0. And then your actual new point that you're going to suggest will be L times X. So this is drawn from zero mean unit variance. And then you take the Cholesky decomposition that you've worked out from the past history of the chain, and then you form a new point. And that will automatically have adapted to the kind of structure that you're seeing in your parameter space, and it'll make it a very good way to jump between regions of parameter space. So it can adapt as the sampling goes on. What this does is make it non-Markovian. So it's no longer a Markov, essentially a Markov chain Monte Carlo, because you're no longer just reliant on the last point, you're reliant on the entire past history of the chain. What you can do is do this adaptation for a while, make sure you've got a good width of your proposal distribution, and then switch off the adaptation from that point on, you will be back to Markovian because you've switched off the adaptation, and now you're now just reliant on the last point. To make this, there's some other tricks that you have to take into account. You have to use the entire past history of the chain. You can't just use a small chunk from the recent past. There's lots of stats and math behind that, which I'm not sure I totally understand. But basically, if you use the entire past history of the chain, then that retains a property called ergodicity. Ergodicity means that by the time the chain is burnt in, you really will be sampling from the true probability distribution of the parameters. If you only use the recent past history of the chain, then you could be biased in some way. There's also single component adaptive metropolis, SCAM, which looks at the covariance structure of the chain, then looks at the eigenvectors of that covariance matrix, and then proposes points along the major eigenvectors of the parameter space. We also draw points periodically from prior. That allows you to explore the edges of parameter space in case you become stuck. And we also have custom sampling groupings. So we're not just sampling in the entire parameter space. If we know that there's some strong covariance between certain groups of parameters and we want to just vary those, then we take that into account. So these sampling groupings are based on our physical intuition of how the parameter space is covariant. And that makes things mix and explore a lot better. So all of this is pretty well tuned, but the code is general. So it will do all of these things automatically. You will have to know your prior space and make your own prior draw functions, which you can actually make a part of this model. You also have to form your own custom sampling groupings. By default, it will just search over the entire parameter space. But all of this makes our MCMC exploration really, really good, I think. Any questions about that? I forgot to put the link to the sampler here, but it's on Justin's GitHub page, and it's fairly intuitive to use. I'm not going to say it hasn't got as many likes or forks as MC, but it's still pretty good, and it's good for our purposes. Okay, now how we detect the gravitational wave background or other single sources in Bayesian inference, that's a model selection problem. So we need to prove that there are spatial correlations between the pulsars. So we compare the Bayesian evidence for a model which includes these Hellions and Downs spatial correlations and one which doesn't. So the model is always going to have some low frequency noise which is common between the pulsars, but it won't be necessarily spatially correlated in the right way. We either switch the Hellions and Downs on or off, and when we eventually claim a detection in the future, it'll be claiming for Hellions and Downs correlations against no correlations. John showed this yesterday, but this is the odds ratio. It's kind of like your betting odds for one model against another. This is the ratio of the evidences. It's known as the Bayes factor. And this is your prior odds ratio, which is by and large just set to 1 in the literature. I'm not sure if I've never seen a paper which actually parametrizes or includes anything different from 1. I don't know if you know of anything. Mm-hmm. Okay. Yeah. Okay. So it actually does come in useful. That's good to know. There are lots of ways of getting this Bayes factor. Multi-nest was a popular version of nested sampling. But for LIGO, it's the version of John's and Alberto Vecchio's that's used. There's thermodynamic integration, which uses lots and lots of these temperatures. So remember the temperatures are when you raise the likelihood evaluation to some inverse temperature. So a really, really high temperature chain will smooth out the parameter space and let you explore the prior volume better. You're going to combine all of that temperature information into an estimation of the Bayesian evidence. So that will give you, multi-nest gives you the numerator or the denominator. Thermodynamic integration gives you the numerator or the denominator. Reversible jump MCMC will just move you between different models, and so you're counting how often your chain spends in the different models. So that directly gives you the either the Bayes factor or the posterior odds ratio. I can't recall. 100. Yeah, it's pretty big. And the techniques that we actually use, or using in the recent past, Savage-Dickey density ratio and the product space method, and they're used for different things. So first of all, Savage-Dickey works great when you've got nested models. So for example, one of the models you might care about might be just noise alone as a description of your data. The other model might be signal plus noise. So in that case, you've got a nested model because noise alone is a special case of the signal plus noise. You need to identify a parameter, or at least a region of parameter space, which essentially switches off your signal. So when you switch off the signal, that makes the likelihood under the signal model identical to the likelihood under the noise model. That's very important. So your Bayes factor for signal plus noise versus only noise is going to be the prior of the amplitude being 0 divided by the posterior of the amplitude being 0. So this is something you already know. This is something you've put into your analysis, or you've put into your MCMC. This is something you actually have to work out from your MCMC chain. And in our case, we can take just the PDF value, the posterior PDF value of the gravitational wave background amplitude at very, very low values. And our sampling is very efficient to get us good coverage down to very low amplitude values. Obviously, we've got no detection, and so we're going to get excellent coverage at values which are consistent with 0. It breaks down in the strong signal regime, because then you won't get very good coverage in the region of parameter space where the signal is 0. This is an example just of doing an analysis of the nanograv 11-year data set. This is the amplitude of the gravitational wave background in log space. I've fixed the spectral slope of the background to be minus 2/3 for a population of circular gravitational wave-driven binaries. And then this is the analysis done under different versions of the JPL model for the solar system ephemeris. There are lots and lots of variations in this, and that's why we're exploring this. But basically, we can make this kind of posterior PDF plot and then look at the low amplitude bins and get from that an estimate of the Savage-Dickey Bayes factor. So what we're seeing here for this particular region of curves, the Bayes factor for signal plus noise versus noise alone is 2.5. So it's very, very weak. You would never try to make any sort of hint of a detection at a Bayes factor of 2.5, because that's kind of saying your odds are 2 or maybe 3 to 1 that you've got a signal in there. That's really, really weak. You want it to get up to something like 100 or maybe 1,000 to 1, and that might even be still weak compared to 5 sigma. Now, that's the previous method. Savage-Dickey is good for signal plus noise versus noise model comparisons. The product space has been good for comparing gravitational wave Hellions and Downs correlations versus no correlations. So there's always signal in there, but what changes is whether you switch on or switch off the spatial correlations. So I was only able to find this in your thesis, John, recently, but it's been in the literature for maybe since the mid-90s. The idea is that your search space is just the union of all of the parameter spaces, the models you care about. So you have to formulate the entire model parameter space to begin with. You then add another model index and variable to your parameter space. So you have something which tells you which sub-likelihood is switched on. When this moves into a particular value for the sub-likelihood, it'll activate the parameters that are in that sub-likelihood and just switch off all of the other parameters that you have. And so all those other parameters which are inactive will just be sampling from their prior, whereas the active parameters will be actually constrained by this sub-likelihood. So again, it's like reversible jump. It's like a poor man's reversible jump, because the relative time spent in each model index value gives you directly the posterior odds ratio. And so we've been using this within the last year or so, and it's worked out very well for us. Is that the same as what you did? Yeah. Okay. Yep. Yep. Mm-hmm. Mm-hmm. Yeah. Yeah. The way we've sort of tackled that is by doing an initial sort of trial run. We then make an estimate of what the Bayes factor is from that trial run, and then introduce a weighting factor which reduces contrast between the models. And then it's sort of an iterative process. It's something I think that our good friend Neil did in a Savage-Dickey context. So I thought it was quite neat to try. Okay. Now that's how we compute things. Sorry? Yeah, my good friend Neil. Yeah, it was pretty cool in a Savage-Dickey context, so we wanted to include it for product space. Now that gives you the Bayes factor, but it doesn't convince people of what a Bayes factor of 3 or 4 really means in their usual way of thinking about it in a frequentist context. So you want to know, if you get a Bayes factor of 3 to 1, how often could you get that Bayes factor of 3 to 1 just from noise processes alone? So this is an unholy alliance of frequentist statistics and Bayesian statistics. You could run many noise simulations to determine the sort of p-value, but we have a data set which might have undiagnosed noise processes in there, and if we do a noise analysis and then we make fake simulations of noise, we might be leaving out stuff that we haven't diagnosed in the original data set. So we want to kind of keep all of the idiosyncrasies in the real data set and operate on the real data set. So we came up with a method which is a combination of sky scrambling and phase shifting. So in this rank-reduced description, this is your Fourier summation of the background to make the dense covariance matrix in the time domain. You can either add random phase shifts. You can either add random phase shifts to all the basis functions, your sine and cosine basis functions, and that screws up the spatial correlations. Or you can scramble the pulsar positions in your model, so again, you've screwed up any possible correlations. And the idea is to make your screwed up simulations or your screwed up operations on the true data set as orthogonal as possible to the Hellings and Downs correlations. So the blue here is when we've done this process by actually doing lots and lots of simulations where you don't have any Hellings and Downs correlations. The red is when we've scrambled the pulsar positions to make a scrambled overlap reduction function, a scrambled Hellings and Downs curve. And the green is when we've done lots and lots of phase shifts, adding random phases to the signal model functions, the signal basis functions. And this is the distribution of the Bayes factor under the null hypothesis. So you're going to get some true Bayes factor from your proper analysis of the data set, and this will be maybe somewhere over here. And so you want to see how often these noise processes alone could actually get you a Bayes factor as large as what you truly have. This looks very, very strong because this is some very strong mock data. So this is a way of us trying to do time slides the way LIGO does it, but with phase shifts and stuff. Yep. Yes. This is all in the presence of a signal. Yeah. Yes, there are a finite number of scrambles. It's actually Jonathan Gare enjoyed tackling this problem, and it's not a solved problem. It's related to some obscure mathematical thing called spherical packing, and it's related to how many cones of a certain angle you can fit inside a hypersphere, which is solved in low dimensions, but it's not solved in general n dimensions. The best we can do here is, it's like trying to overcome your autocorrelation length. Just try to produce as many as possible to overcome any local clumpiness in these distributions. Okay, and because I thought it would be quite cool to include a probabilistic graphical model, this is the probabilistic graphical model for pulsar timing arrays. If you're unfamiliar with these, the square box shows you that you have an array of pulsars, and so your likelihood or your probabilities will be the product over all of these pulsars. This is showing the conditional dependencies of the time of arrival measurements on all of the different processes that you have. So you'll have some white noise time series, which depends on the white noise variance. You'll have some timing model time series, which depends on your timing model parameters, like the period and the spin down of the pulsars. You'll have some intrinsic red noise per pulsar time series, which depends on the Fourier coefficients, which in turn depend on the variance of the coefficients, which in turn depends on the amplitude and the spectral index of your model. Likewise, you'll have a gravitational wave time series, but that will cover all of the pulsars. You'll have some variance of the gravitational wave coefficients, and that'll depend on the amplitude background, the eccentricity of the population, which can produce a turnover in that spectrum, all of the physics I've talked about. And you'll also have some angular power distribution dependence in the background. That'll depend on whatever model you use to decompose that. In this case, this is the spherical harmonic decomposition. So that's pretty much all I had to say and that I wanted to talk about. I'd like to know if there are ways to overlap with what LIGO and Lisa are doing, or if any of this stuff is shared by what you're doing. Are there people tackling the stochastic background in LIGO with Bayesian methods? Yes, anything like that. Okay. Mm-hmm.